Okay, so let's dive in. We're all, swimming in information these days, right? Articles, research, prepping for
It's
meetings.
overwhelming.
Totally, just this endless current. And the big question is, how do you actually cut through all that noise?
Hmm.
How do you get to the really important stuff, the key insights, without just, well, drowning?
Exactly.
So that's really our mission for this deep dive. We're looking at something genuinely groundbreaking.
Yeah, a new system for organizing, for retrieving data.
And it's not just about speed, is it? It's something deeper.
Right. It's about making complex data inherently understandable, almost
Uh,
self-documenting, you could say.
Self-documenting. Okay, that sounds intriguing.
It is. It's about pulling those crucial nuggets of knowledge, those insights, out of that huge ocean of data, giving you those aha moments you often miss.
Yeah, those moments are gold.
So our goal here is to really show you how this invention tackles a fundamental problem. We want to unpack its ingenious solutions.
And explain why it's potentially such a big deal. Why it could redefine how computers, well, think.
Precisely, how they interact with information at a really basic level.
Okay, let's set the stage then before we get into the solution. What is that fundamental challenge? The big problem this is trying to solve.
Well, the core issue, really, is that modern computing systems, powerful as they are, they really struggle. They struggle to organize and retrieve data from these incredibly complex, multidimensional spaces.
Right, like data with lots of different facets or characteristics.
Exactly. And they need to do it
Mm,
efficiently,
yeah.
and you need to be able to understand why you got a certain result. Interpretability is key.
Which sounds like a tall order.
Yeah.
Finding a specific thought in, like, a global brain that's always changing.
That's a good analogy, actually. It's a bit like that.
So we do have tools already, obviously.
Yeah.
What are they and why aren't they, cutting it?
We do, but they all have significant limitations. Take traditional geometric indexing, for example, things like Hilbert curves.
Okay.
They try to map complex data onto simpler patterns, but these patterns are fixed. They don't carry real semantic meaning, what the data is about.
So they don't understand context.
Not really.
Yeah.
They can't adapt easily when the data itself changes, and critically, they offer zero explainability. You get data back, but no reason why. They're like a rigid map laid over a landscape that's constantly shifting underneath.
Okay, so precise in a way, but dumb. What about things like tree-based structures? We use those all the time. B trees, R trees.
Yeah, and they're great for simpler stuff, maybe one dimension, like sorting numbers or text. But they often have fixed branching factors,
Meaning,
meaning how they split the data isn't based on the actual importance or relationships within the data. It's just a predefined structure. And they really struggle with connecting ideas across different dimensions or categories.
right. So if you want to link, say, a customer demographic to a product preference and a purchase time, trees get complicated.
Very complicated,
Mm.
or just can't do it effectively. Then you have knowledge graphs and semantic networks.
Which are all about meaning and connections, aren't they?
They absolutely are. They excel at representing those rich relationships. But their structures can often be quite arbitrary, almost bespoke,
Okay.
which makes them hard to systematically break down or partition for efficient processing, especially on parallel hardware. They don't have that inherent spatial locality.
Meaning it's hard to know which bits of the graph are close to each other computationally.
Exactly. And they often lack a clear, consistent hierarchical organization for drilling down into details progressively.
All right, so what about the really modern stuff? Neural embeddings, vector databases, the engine behind a lot of today's AI.
Yeah, incredibly powerful for certain tasks,
Yeah.
like similarity matching. But they work with continuous representations, these dense vectors,
Which means?
which means they can suffer from semantic drift. The meaning can subtly shift over time as the model retrains, often in unpredictable ways,
Okay.
and they're often the ultimate black boxes. You put data in, you get an answer out, but tracing the why, it's incredibly difficult, if not impossible.
So no easy explanation.
Right. No structural guarantees for stability, and the computations, especially finding similarities in huge data sets, can be really computationally expensive.
Wow. So even with all that tech, it feels like there's this big gap. No single solution seems to tick all the boxes.
That's precisely it. You look across the board, geometric indexing, trees, graphs, vectors. None of them simultaneously give you mathematically guaranteed search performance, constant time explainability.
Constant time meaning it doesn't get slower as the data grows.
Exactly, independent of data volume. Plus, you need hardware efficiency, parallel processing, semantic stability, addresses that actually mean something, a consistent way to rank everything by importance, and crucially, this idea of unifying data points in the containers they sit in.
That's a heck of a wish list.
It is, and that's the fundamental gap this invention really aims to fill.
Okay, so that paints a clear picture of the challenge. What's the breakthrough then? What's the core idea that, cracks this code?
The core solution is what we're calling a hierarchical, multidimensional semantic indexing system. And the absolute keystone, the central concept, is a new parameter. We call it E.
E. Okay, what does E represent?
Think of E as the total depth of organization across all the different ways you categorize your data. So if you have, say, 3 dimensions, and one has 4 levels of hierarchy, another has 3, and the last has 5, then E is 4 plus 3 plus 5. E is 12.
So E is the sum of the depths across all dimensions.
Exactly. It's a measure of the total hierarchical complexity you've defined for your data space.
And why is that number E so important?
Because it becomes this master control dial for the entire system. It simultaneously dictates the factor by which search complexity is reduced. We're talking exponential reduction. It guarantees that constant time explainability, the path to understanding, is always proportional to E, never the total data size. It also defines a potential for hardware parallelism, and even dictates the size of the metadata needed at each point in the hierarchy. You get predictability, efficiency, explainability, all governed by this single, understandable parameter E.
That's actually quite elegant, controlling all those critical aspects with one measure. So E sets the structure, but what's the engine inside? What actually makes it work dynamically? You called it the beating heart.
Yes, the beating heart is the consistent weight block rank algorithm. This is where the real algorithmic magic happens.
Okay, break that down. Consistent weight block rank.
Right. Imagine you're organizing a massive, constantly changing library. But you're not just sorting by author or title. You're sorting everything, every book, every shelf, every section, based on its current importance or relevance, determined by dynamic weights.
Importance based on what? Connections,
Yeah.
user interest.
It could be based on connections, frequency of access, machine learning predictions, synergy between topics. The point is, it's dynamic. And crucially, the same ranking rule applies to everything. A single data point, a node, follows the exact same weight-based sorting logic as a whole group of data points, a block.
So nodes and blocks, data points and their containers are treated identically by the ranking system.
Identically. It applies this recursive weight-ordered prioritization throughout the entire hierarchy. It ensures that related things stay close together, semantic locality, but the ordering is purely based on calculated importance, not some fixed alphabetical or structural rule.
And this is constantly adapting.
Continuously. It's like a dynamic pulse adapting to data changes, capturing what we call synergy weights, the extra importance generated when different elements interact. This enables really intuitive navigation patterns. It's even explicitly optimized for things like chat context and coaching AI, where understanding the flow and weight of a conversation is vital.
That unification of nodes and blocks sounds really key. And you mentioned hardware playing a big role, this semantic address bus.
Yes, this is a fundamental piece, a true hardware-software co-design element. Imagine if every piece of data had an address, but that address wasn't just numbers and letters, it told you what the data was about.
Like a meaningful address.
Exactly. These multidimensional coordinates, these prefixes, serve dual purposes. They act as routing information for the hardware to find the data, and they simultaneously function as self-documenting semantic labels. You know the context just by looking at the address prefix.
Okay, that's clever.
And it gets better. These same address bits can directly control skip logic signals for memory banks. If a query doesn't match a certain prefix, the hardware can power down entire sections of memory, saving enormous amounts of energy. It's a true dual-purpose bit system.
Wow. So the address itself routes, explains, and saves power. But if it's also dynamic, based on weights that are constantly changing, how do you stop the meaning from just drifting away? How do you maintain stability?
Ah, good question. That's handled by the threshold-based stability mechanism, instead of letting meanings shift continuously and subtly, which leads to unpredictability.
Right, like that semantic drift in vector databases you mentioned.
Exactly. This system uses discrete reclassification. Changes in categorization or meaning only happen when aggregated weights cross predefined thresholds.
So only significant shifts trigger a change.
Precisely. This makes the system's state transitions clear and auditable, really important for compliance or debugging. And it keeps the update cost manageable, proportional to E, ensuring the system remains predictable over time.
Okay, stable, explainable, efficient. And then there was this other piece, the multiplicative pruning via orthogonal decomposition. That sounds like the heavy-duty math part.
It is, but it's the engine behind the exponential search reduction. Essentially, this mathematical framework lets us break down an n-dimensional search problem. Instead of exploring, say, t possibilities in each of n dimensions, which gives you t to the power of n total combinations, a huge number.
Right, the curse of dimensionality.
We reduce it to exploring only c possibilities per dimension, where c is much, much smaller than t. So the search space shrinks from Tn down to Cn.
And that reduction multiplies across dimensions.
It multiplies. This framework achieves linear information gain to Geeden. You learn more from each step of the search. And it allows for highly parallel processing across these decomposed dimensions with minimal interference or crosstalk. This directly enables that hardware skip logic we talked about, giving you massive power savings, often over 93%, especially for sparse queries where you're looking for rare combinations.
It's like the system geometrically pinpoints the relevant area and ignores almost everything else.
That's a great way to put it. Collapses the haystack around the needle.
Okay, so let's get into the nitty-gritty. How does it actually assign these coordinates and weights? What's happening under the hood?
Well, every single data element gets one of these multidimensional semantic coordinates. It's a tuple, like PO, where each pen is a prefix code from the hierarchy in dimension I.
And these prefixes are the meaningful addresses.
Exactly. They are self-legending. The prefix itself tells you the path through the hierarchy, explaining the context. Region.NorthAmerica.USA, California tells you more than just a zip code.
Sure.
They provide hierarchical inheritance, so child concepts automatically inherit properties from their parents. And they allow for powerful cross-dimensional intersections. Just combine prefixes. Product.electronics.mobile, intersected with region.asia. Japan finds mobile electronics relevant to Japan.
And the weights, how are those importance scores calculated? Is it just arbitrary?
Oh, not at all. It's very data-driven. The weight function calculation methods can use several approaches. It might be based on statistical correlations, how often things appear together. It could be frequency-based, how often something is accessed. Or the weights could even be derived directly from machine learning models that predict relevance or importance.
So it learns what's important from the data itself.
Yes, and the specific method is chosen to optimize both explainability and search performance for the task at hand.
You've really emphasized this isn't just software. Tell me more about the hardware-software co-design. You mentioned the memory controller.
Right, the prefix-aware memory controller is key. It's specialized hardware that understands these semantic address prefixes. It doesn't just see addresses as meaningless numbers, it sees the semantic structure.
And uses that to save power.
Exactly. By matching query prefixes, it can actively power gate or turn off entire memory banks that contain irrelevant data subspaces. That's a huge part of achieving that 99.2% power reduction figure we see in some applications.
That's incredible. And what about the processing side? How does it leverage different kinds of chips?
It's designed for diverse parallel processing architectures. On standard multi-core CPUs like Intel Xeons, it can use advanced instructions like AVX512 to perform many prefix comparisons simultaneously.
Okay.
On GPUs like NVIDIA's H100, the tensor cores can massively accelerate the matrix operations, often involved in calculating or applying those dynamic weights.
Hey.
On FPGA's field-programmable gate arrays, like Xilinx Versal, you can build custom hardware engines specifically designed for the weight comparison and ranking logic, making it incredibly fast and efficient.
So specialized circuits.
And perhaps most excitingly, it's well-suited for emerging neuromorphic hardware, like Intel's Loihi chips. These brain-inspired processors are incredibly power efficient. We're talking maybe a milliwatt to simulate thousands of neurons, achieving potentially 1,000 times the energy efficiency of a CPU for these kinds of tasks.
Wow. That really opens up possibilities for edge devices and wearables.
Absolutely.
Okay, so putting it all together, the E parameter, the beating heart algorithm, the semantic bus, the pruning, this deep hardware integration. This leads us to the aha moment. What are the headline results, the performance metrics that really make you sit up and take notice?
Well, the search complexity, as we discussed, is dramatically reduced, scaling incredibly well. But the absolute game changer, I think, is the explainability. It's OE.
Constant time based on that E parameter.
Yes. Regardless of whether you have 1 million records or 1 trillion, understanding why you got a result involves tracing at most E hierarchical steps. There is fundamentally no black box. You always have a transparent, traceable path.
That alone is huge for trust, for debugging, for regulation.
Absolutely monumental.
Yeah.
And then the efficiency numbers are just staggering. We see things like a 762 times reduction in memory cache line reads compared to traditional methods in certain benchmarks.
700 times fewer memory accesses?
Yes, because the system knows exactly where to look.
Yeah.
And the power efficiency we've measured up to 55,294 times power efficiency improvement in specific scenarios, largely driven by that 99.2% power reduction from the unified skip logic gating on both blocks and nodes.
55,000 times. That's hard to wrap your head around.
It really changes the equation for where you can deploy this kind of intelligence, especially in power-constrained environments like edge devices or sensors.
And how does it scale if I throw more processing power at it?
It offers linear weak scaling up to potentially E times CTN cores. That means you can add more processors and get a proportional increase in throughput up to the theoretical parallelism limit defined by E and the pruning factor. And the metadata size per node remains constant, regardless of the total data volume.
Okay, that's efficient scaling. Now, you mentioned something really interesting earlier. Orthogonal nodes and mathematical symbologenesis. That sounded potentially profound. How does that link to making data understandable and dealing with blind spots?
Right. So when different aspects of your data are statistically independent, what mathematicians call orthogonal, the system can essentially treat them as if they create entirely new dimensions of understanding.
Because they don't influence each other.
Exactly. There's no correlation pulling them together. The beating heart algorithm ensures that the data within these orthogonal subspaces still forms these uniform, geometrically predictable n-dimensional shapes or blocks.
So the structure remains consistent even across independent aspects.
Yes. And this consistent geometry, combined with the orthogonality, allows the system to multiply its pruning effect. The efficiency gains become exponential.
Okay.
This leads to what we term mathematical symbologenesis. Symbologenesis means the birth of symbols. Here, the system takes your vast, high-dimensional data space and geometrically compresses it into these incredibly dense, yet highly structured, self-documenting symbols, those prefix coordinate tuples.
So each coordinate isn't just a label, it's like a compressed representation of a whole region of the data space.
Precisely. A single symbol, a single coordinate tuple, becomes a fixed point in this geometric space that efficiently encodes potentially millions or billions of underlying possibilities. They become instantly accessible concepts.
And that ties into sailing faster than the semantic wind.
Yes, because the system is exploiting this underlying geometric independence, this orthogonality. It achieves performance gains that seem to exceed the apparent complexity of the data itself. It's getting superlinear returns by leveraging the geometry.
Okay, I think I'm following. The structure lets it be smarter than just brute force.
Right. Now, the information density packed into these symbols can actually exceed what a human could make sense of if you just looked at the raw coordinates. It's too compressed. But the beauty is, the system's uniform geometry organizes, or herds, this complexity into navigable clusters. And critically, it makes the blind spots into aware blind spots.
Aware blind spots, what does that mean instead of just missing things?
Instead of a black box model just ignoring possibilities without telling you, this system explicitly represents the regions it pruned or skipped. These aren't errors. They are choices made by the algorithm based on weights and relevance.
So you can see what was considered less important or irrelevant.
Exactly. The blind spot isn't hidden. It's symbolized, often with metadata explaining why it was pruned. Example, weight below threshold, statistically insignificant intersection. This transforms potential pitfalls into transparent conscious trade-offs. You can choose to explore those less likely paths if needed.
That turns a weakness of other systems into a strength here. It fosters trust and maybe even serendipity, letting you explore unexpected corners.
Precisely. It makes the system's reasoning, including what it didn't prioritize, visible and actionable.
This is incredibly powerful. Let's ground it in the real world. How does this actually solve tangible problems? Give us some examples.
Okay, let's take a medical diagnosis system. Imagine you have dimensions like symptoms, maybe hierarchy level L4, patient demographics, L3, and lab test results, L-seat. The total E value is 12.
Right.
Now, a clinician asks a complex query. Find potential respiratory conditions in pediatric patients who also have abnormal complete blood count results. This maps directly to a semantic coordinate, say symptom prefix.resp, demo prefix.pediatric, test prefix.abnormal CBC.
Okay.
The system, using its structure, might only need to explore, say, 0.0012% of the total theoretical search space, and crucially, it provides an instant explainable path. The system focused on breathing issues, narrowed to children, then cross-referenced with blood anomalies.
And that's super fast and transparent for the doctor.
Exactly. We're seeing potential for things like 361 times improvement over conventional database searches in such scenarios, with full auditability.
Huge for healthcare. What else?
Think about financial risk assessment. Dimensions like market sectors, LO5, specific risk factors, L4, time periods, L3, again, E12.
Hmm.
This allows for real-time aggregation of complex, multifaceted risk. You get explainable audit trails for regulators. They can see why the system flagged a certain risk profile. And we see potential for things like a 95% reduction in the computation needed for backtesting trading strategies.
Wow, 95% faster backtesting is massive for finance.
Okay, another one. Let's look at supply chain optimization, notoriously complex. You might have geographic regions, L5, product categories, L4, time horizons, L3, and maybe supply risk factors, L4. Here, E16.
A deeper hierarchy.
Yes. In simulations, this system achieves things like an 847 times reduction in search complexity due to that unified block node ranking. We're talking query latencies around 12 milliseconds with 99.7% accuracy in finding optimal solutions.
That's near real time for a global supply chain.
It is. And it naturally integrates those synergy weights, like how demand for raincoats in the Pacific Northwest spikes in winter. It also explicitly handles empty subblocks, areas with no inventory within the same unified ranking system, avoiding errors.
You mentioned chat context.
Right, the optimization for chat context in a system coaching a supply chain manager could reduce the latency in conversational query responses by maybe 73%. Overall, we're looking at potentially 3,750 times improvement compared to traditional ERP systems for specific complex query types.
That's transformative. Okay, one more critical application, maybe something cutting edge.
How about brain-computer interfaces, BCI? This really highlights the efficiency and potential human impact.
Wow, okay.
Imagine you're processing signals from, say, a 124-channel neural implant. Using FPGAs like the Xilinx Zinc Ultrascale plus ORD, the system can go from raw neural signal acquisition to a meaningful semantic output like identifying the user's intended movement in less than 5 milliseconds.
Less than 5 meters,
Yes.
compared to what usually.
Compared to maybe 50 to 200 milliseconds for more traditional processing pipelines. And it can achieve high accuracy, say 94.7%, for classifying 4 different motor imagery tasks, with an extremely low false positive rate, less than 0.1%.
That speed and accuracy is life-changing for prosthetics or communication aids.
Absolutely. And the power efficiency is critical for anything implantable. We're talking maybe 1 milliwatt per 1,000 neurons processed potentially 1,000 times more energy efficient than doing it on a standard CPU.
So feasible for long-term implants.
Yes. And here, the aware blind spots concept is incredibly powerful. The system can show clinicians which neural patterns or signals were deemed less relevant and pruned.
Mm.
This turns those potential gaps in understanding into aware trade-offs. Clinicians can see what the system focused on and why, make informed ethical choices about tuning parameters, or even explore those less obvious neural patterns that might hold unique insights for that specific patient. It enables real shared decision-making.
That's incredibly profound. Okay, this all sounds revolutionary. So the big question is, if it's this good, why hasn't someone done this before? Why is it considered a non-obvious breakthrough?
Well, interestingly, prior art and conventional wisdom in computer science actually taught away from this approach in many ways.
Really? How so?
For instance, traditional indexing often viewed depth-first traversals, going deep down one branch before exploring others, as inefficient for broad searches. You risk getting lost down an irrelevant path.
Okay.
And weight-based priority systems, while they exist, often shied away from imposing strict, deep hierarchies because it adds complexity. Furthermore, the idea of unifying blocks, data containers, and nodes, data points, under a single dynamic, weight-based ranking rule, there was really no prior teaching suggesting that was feasible or stable. It seemed overly complex.
So people thought combining these ideas wouldn't work or would be too hard.
Exactly. The perceived complexity, the potential instability of managing different elements with one dynamic rule, the computational cost, especially with synergy effects, it all discouraged this unified approach.
A classic case of needing to combine seemingly disparate or even counterintuitive ideas.
Precisely.
Mm.
And the results turned out to be unexpectedly synergistic. The performance gains you get from combining these elements, especially the beating heart algorithm with its block node unity and dynamic ranking, are multiplicative. They far exceed what you'd get by just adding up the benefits of each component individually.
Like the whole is much greater than the sum of its parts.
Much greater. That 847 times search reduction, coupled with OE constant time explainability, that combination just wasn't seen as possible with, say, weight-only systems. We see huge practical differences, too, like cache hit rates jumping from maybe 23% in a weight-only system to over 94% with this unified approach.
That's a massive practical difference in performance.
It is. And there's also a domain-specific non-obviousness. Think about highly regulated fields like finance or medicine. You need to understand the full context of a primary factor, the main symptom, the biggest risk before you even consider secondary factors.
Semantic completeness is vital.
Exactly. Prior art didn't really have a robust mechanism to enforce that kind of semantically complete, priority-driven exploration within a hierarchical framework. This system provides that.
Okay, this deep dive has really painted a picture. It feels like we're moving from just storing data to creating data environments that have an inherent understanding, an inherent structure.
That's a great way to put it. This shift transforms that feeling of information overload into potentially an empowering landscape of genuine understanding by mathematically proving how this specific type of spatial geometry can give birth to these dense, meaningful symbols.
The symbologenesis.
Right. And then leveraging hardware co-design to navigate that geometry efficiently, to sail faster than the semantic wind by exploiting orthogonality.
Mm.
It makes incredibly complex decisions traceable, explainable, and efficient in a way that truly unlocks insights that were hidden before.
It's like the structure itself distills the density.
Yes, the uniformity allows orthogonal dimensions to intersect and herd that complexity. It
Hmm.
compresses information so effectively, it goes beyond raw human sense-making capacity, yet the structure makes it navigable, affording meaningful choices.
It leaves you with a pretty provocative thought, doesn't it? Imagine a future where data doesn't just sit there, but it understands itself within this kind of framework.
Hmm.
And where those blind spots, the things you don't know or haven't considered, aren't hidden dangers, but become visible, flagged invitations to explore new possibilities. How could that level of built-in interpretability and guided choice change how we make decisions, not just in tech, but in medicine, science, policy, the really critical areas?
It really could reshape our entire approach to knowledge discovery and decision-making in very fundamental ways.